The digital world projects an illusion of weightlessness. When you type a prompt into an interface, the response feels instantaneous and ethereal, as if pulled from a frictionless void. But artificial intelligence is deeply physical. It is forged in steel, silicon, and massive amounts of electricity. The intelligence that writes code, drafts legal briefs, and generates art is anchored to sprawling industrial complexes that consume resources on a scale rarely comprehended by the end user. At the heart of this physical reality are large language models. These complex mathematical architectures learn the patterns of human language by analyzing vast oceans of text. The process of teaching these models, known as the training phase, requires reading and processing trillions of words over and over again. To achieve this, the algorithms adjust up to 175.0 billion internal parameters in earlier iterations, mapping the probabilistic relationships between words, concepts, and ideas. This monumental computational task is driven by specialized hardware, predominantly NVIDIA GPUs. Originally designed to render video game graphics, these chips proved exceptionally adept at the parallel processing required for machine learning. Today, they are stacked by the tens of thousands inside massive cloud data centers. These facilities are the engines of the modern AI boom, operating around the clock to crunch the data that makes generative AI possible. The sheer scale of these operations translates into staggering energy consumption. Training a single, state-of-the-art model can take months of continuous computation. During this time, the servers draw megawatts of power, operating at maximum capacity. The electricity required to train one flagship model can easily equal the annual energy usage of over 1,000 average households. The reason for this massive power draw lies in the mechanics of backpropagation. As the model attempts to predict the next word in a sequence, it constantly compares its output to the actual training data. When it makes an error, the system calculates the difference and sends a signal backward through the neural network to adjust the weights of its connections. This microscopic mathematical correction happens billions of times per second, and every single calculation requires a tiny burst of electrical current. The trajectory of AI development has dramatically amplified this demand. The estimated energy used to train early iterations like GPT-3 was significant, but the subsequent generations have scaled exponentially. The industry has largely operated on the assumption that scaling up data and compute directly yields better performance. This scaling law has triggered an arms race among technology giants, leading to the construction of unprecedented computing clusters. This insatiable hunger for electricity inevitably leads to a massive carbon footprint. The environmental impact of a data center is inextricably linked to the local power grid it relies upon. If a massive computing facility is located in a region where electricity is generated primarily from coal or natural gas, the training process pumps thousands of tons of carbon dioxide into the atmosphere. The pursuit of artificial intelligence becomes directly tethered to fossil fuel extraction. The strain on infrastructure is becoming impossible to ignore. In regions with high concentrations of data centers, grid operators are warning of potential power shortages. The sudden massive load additions required by new AI facilities are forcing utility companies to delay the retirement of older fossil fuel plants, complicating national and regional efforts to transition to renewable energy sources. Yet the environmental cost does not end when the training is complete. Once a model is deployed to the public, it enters the inference phase. This is the process of generating responses to user prompts. While a single inference uses a fraction of the energy required for training, the cumulative impact of millions of simultaneous queries is immense. Comparing a traditional web search to an AI query illustrates the shift in resource intensity. A standard search retrieves existing information from an indexed database, requiring minimal computation. An AI query, however, forces the model to generate a unique response in real time, calculating probabilities across its entire neural network. This generative process can consume up to 10 times more electricity per interaction than a conventional search. Electricity is only one part of the environmental equation. The dense concentration of high-performance computing equipment generates an immense amount of heat. To prevent the servers from melting down, cloud data centers rely on extensive cooling systems. While some use advanced air conditioning, many rely on evaporative cooling towers, which consume millions of gallons of fresh water. The hidden cost of this water usage is becoming a critical issue in arid regions, As tech companies build facilities in areas with cheaper land and electricity, they often place massive demands on local watersheds. The depletion of local water tables to keep servers cool presents a stark conflict between technological advancement and basic human and ecological needs. These realities are colliding with the public sustainability commitments of major technology corporations. Over the past decade, many tech giants made ambitious pledges to become carbon neutral or carbon negative. However, the rapid integration of generative AI into their core products has caused their greenhouse gas emissions to spike, pushing those climate goals further out of reach. In response to this growing crisis, the field of green AI has emerged. Researchers are actively seeking ways to decouple intelligence from massive energy consumption. This involves developing more efficient neural network architectures that can achieve similar performance with far fewer parameters. Techniques like quantization reduce the precision of the mathematical calculations, significantly lowering the power required without severely degrading the model's output. Hardware developers are also pivoting. While the current generation of NVIDIA GPUs dominates the training phase, a new market is opening for specialized inference chips. These processors are designed specifically to run pre-trained models with maximum energy efficiency, aiming to reduce the power draw of the millions of queries happening every second. The location of future data centers is also undergoing a strategic shift. To mitigate their carbon footprint, companies are increasingly seeking to co-locate their facilities directly adjacent to renewable energy sources. Building data centers next to massive solar farms or geothermal plants ensures that the power drawn is clean, though the intermittent nature of solar and wind presents challenges for servers that must run constantly. This need for continuous, zero-carbon baseline power has sparked a sudden and intense interest in nuclear energy within the tech sector. Major cloud providers are exploring partnerships with nuclear power operators, and some are even investing in the development of small modular reactors. The idea is to build dedicated, emission-free power plants solely to fuel the next generation of AI training facilities. There is a profound paradox at the center of this environmental debate. Artificial intelligence holds immense potential to be a crucial tool in fighting climate change. Advanced models are being used to optimize power grids, discover new materials for better batteries, and model complex climate systems with unprecedented accuracy. The technology could accelerate our transition to a sustainable future. However, the tool we are building to solve these massive planetary challenges is currently exacerbating them. The net environmental benefit of AI will depend entirely on whether its application in climate science and energy optimization can outpace the massive carbon and resource footprint of its own creation and operation. The foundational principles of those early AI breakthroughs still guide development, but the scale has fundamentally altered the stakes. We are no longer just writing code in a laboratory, we are reshaping global energy infrastructure. The assumption that we can simply build larger models by throwing more power at them is crashing into the physical limits of the planet. This collision is driving a search for entirely new paradigms in machine learning. Researchers are exploring neuromorphic computing, which attempts to mimic the extreme energy efficiency of the human brain. The human brain, despite its immense cognitive power, operates on roughly 20.0 watts of energy. Bridging the gap between biological efficiency and synthetic computation is the next great frontier. Until those revolutionary breakthroughs arrive, the industry must navigate the current reality of resource-intensive computing. Transparency is becoming a critical demand. Researchers and policymakers are calling for standardized reporting on the energy consumption and carbon footprint of specific models. Just as consumer appliances have energy efficiency ratings, there is a push for AI models to carry environmental impact disclosures. This push for transparency may soon become a regulatory requirement. Governments are beginning to draft legislation that would force companies to disclose the environmental cost of their AI operations. By making the invisible energy drain visible, regulators hope to incentivize the development of leaner, more efficient models and discourage the reckless consumption of resources for marginal gains in performance. The future of artificial intelligence cannot be separated from the future of energy. The next phase of innovation will not just be measured by how many parameters a model possesses or how human-like its responses appear. It will be measured by its thermodynamic efficiency. The smartest models of the future will be those that achieve brilliance without burning the world to do so. The environmental impact of training large language models is the defining physical constraint on the digital revolution. As we push the boundaries of what machines can understand and create, we are forced to confront the material reality of our ambitions. Balancing the profound promise of artificial intelligence with the urgent need to protect the planet is not just an engineering challenge, it is the most critical test of our technological maturity.